Okay, this is RL Circuits video 3. This is the second time I'm making this video. My voice sounds angry. It's because I hate InterWrite. This program is garbage sometimes. So I have to remake this video and the next video because it didn't record. Anyway, so RL Circuits video 3 is all about time constants actually. In the last video I tried to run through this part again and just say, hey, I rushed in video 2 to talk about what happens at the end of to make sure that our result matches our predicted of what should happen. We'll do that for 1 minute and then we'll go forward. At t equals 0, our voltage drop should be e to the 0. E to the 0 is 1, so my voltage drop across the inductor should start off as EMF. And at t equals infinity, this is e to the negative infinity. At 0, my voltage at the end should end up being 0, so that works. Okay. Well, what we want to talk about next is what the time constant is for this kind of circuit, for an RL circuit. This video is really focused on time constants. For an RC circuit, all of our formulas, all of our expressions for how current or voltage or charge on that capacitor varied with time, all ended up with this nice neat e to the negative t over RC component. And that RC we called something special. We called it funky t, which was the time constant. All right, well, for an RL circuit, we have a time constant just as well. In the RC circuit, it's kind of an intuitive thing. It says that as you increase the amount of resistance in this circuit, it's going to take longer to fully charge a capacitor because the current flows slower through the circuit because you've got more resistance. With the capacitance side, it says it's going to take more time again because the bigger the capacitor, the more charge it can hold, the longer it's going to take to fully charge. RL circuit's not quite so intuitive. In fact, I may not even, depending on the length of this video, go into it at all. We'll just talk about it when we have class next. What I do want to do is at least arrive what the time constant is. So coming from this part, I have the expression e to the negative r over L times time. Okay, the negative r over L times time piece, that's the part that's going to have that time constant in there someplace. Well, negative r over L times time can be rewritten really as negative 1 over the fraction L over r times time. And if you want to check to make sure that makes sense, just multiply the top and bottom of this by r over r. A clever form of 1, your math teacher would call it. And those r's would cancel, and so I'd be left with negative r over L. So this is really negative r over L times time is really negative 1 over the quantity L over r times time. This is the time constant for an RL circuit. The time constant is still funky t, but for an RL circuit, it is L over R. And we'll talk about maybe getting us some ways to think about why it's L over R when we have class next. That's video 3.